Hello, I'm Anand Jain from Hanumangarh, Rajasthan. Welcomes you to your favorite Shridevi Classes YouTube channel, where we inculcate interest and confidence in science and engineering education. Today in our playlist, Electric Circuit, we'll study Ohm's law and understand the property of resistance and resistivity. Let's start. In metallic conductor, these outer orbital electrons are loosely connected to respective nucleus of atom, and nucleus and inner orbital electrons acts like a metallic ion, and these free electrons behave like a gas atom in a room, and these free electrons, by the energy of thermal agitation in metallic conductor, can roam randomly within metallic conductor just like gas atom in a room. Since electron got a very small inertia, the thermal random motion of free electrons got a very high velocity, but in a very small time interval, 10 raised to power minus 14 second, as an electron surpass 5-10 atoms, it get collided with other electrons and divert its direction, and the perfect random motion of electrons results in no net charge transfer by this random thermal motion of free electrons. When external source voltage or an EMF or a potential difference is applied across L length of a conductor, that source voltage establish an electric field in conductor, and electric field is directed from high potential to low potential in conductor, and electron, being negatively charged particle, will experience force and acceleration, and they start a drift motion in opposite direction of electric field as shown here, and this electron drift movement contribute charge transfer. This charge transfer by drift motion of electron in an electric circuit by applied potential involve work done in electric circuit, or this source EMF provide energy to the circuit, and we say EMF or electromotive force of a source is the strength which is measured in unit volt, and numerically it is work done in circulating 1 unit charge all along this closed electric circuit. So work done per unit charge is known as measurement of voltage, and voltage in volts is work done in joule per unit of charge transfer in coulomb. So joule per coulomb is measured in terms of volt as magnitude of source voltage. In any electric circuit, amount of work done in moving a 1 unit positive charge across two terminal of an circuit element is called potential difference across that circuit element, and the potential across any circuit position is measured by a voltmeter which is connected across two terminals in parallel to circuit element. An ideal voltmeter got an infinite resistance, and such ideal voltmeter doesn't draw any current through itself, and current along circuit remain same irrespective of voltmeter connection, and such voltmeter directly measure potential difference across circuit element in volt unit. In previous chapter of electrostatics, we have studied that source electric charge remains stationary and produce electric field surrounding it and exert force on other charges placed nearby. And we have also studied the concept of potential difference and calculation of work done when a charge is moved from one position to another position in electrostatic field. But in current electricity, in this chapter, when we apply potential source across any metallic conductor, these free electron of metallic conductor will start drift motion in one particular direction, and that drift movement of electron involve flow of charge. We know the amount of charge on one electron is 1.6 into 10 raised to power minus 19 coulomb, which is the least amount of charge available in our universe, and charge is measured in coulomb unit, and that coulomb unit is abbreviated as capital C. And if in an electric circuit, if n number of electron will drift from one position to another position across a certain cross section area, then the total amount of charge of those n electron would become Ne, where E is charge of one electron and E is 1.6 into 10 raised to power minus 19 coulomb numerically. And if the number of electron drifted across any section are 6.25 into 10 raised to power 18, a huge number, then that number with small amount of electronic charge will make 1 coulomb charge. So amount of charge of one electron is very small, but the number of drifting electron could be huge, and they can make a good amount of charge transfer by this drift movement of free electron in metallic conductors. In current electricity, when we apply a potential difference across a conductor, the drift motion of free electron in a specific direction cause current flow in circuit. In fact, current in circuit is nothing but flow of charge in closed electric path, and numerically current is amount of charge transfer in 1 unit of time, or charge transfer in coulomb per second is current. A charge is measured in coulomb and time in second, so current have a unit coulomb per second, and we give another abbreviation to current unit as ampere. Mary Ampere has done significant work in study of current and its magnetic effect. So we can say 1 ampere current is that current which results from transfer of 1 coulomb charge in 1 second. Now if current is not a steady magnitude but a time varying quantity, then in place of capital I it is represented by a symbol small I, and time varying current is represented in derivative form, and it is first derivative of charge with respect to time, or we can say current is rate of charge transfer with respect to time, and one can find out current magnitude by calculation of total amount of charge transfer and dividing that by time taken for that charge transfer. One interesting fact about conventional direction of current and direction of drift electron flow is opposite to each other, and the fact is that conventional direction of current was assumed well before the knowledge of atom or electron. The historic fact is that in the year 1801, Volta found first practical source of electric current in terms of voltaic cell, where in a solution of dilute sulfuric acid, when two copper and zinc rods are immersed, the current start flowing in external circuit, and it was assumed that current is flowing from copper to zinc in external circuit as shown here in this conventional direction. And in the year 1897, J.J. Thomson discovered electron by his famous cathode ray experiment, and it was discovered that in our circuit electron drift movement is opposite to the conventional current direction we have assumed from copper to zinc in this external circuit. And now it was decided that conventional current is flow of positive charge, and electron treated as negative charge moves or drift in opposite direction of conventional current direction. And the fact is that there is nothing positive charge which moves in our electric circuit. It is only these electrons drift which makes charge transfer or current phenomena in electric circuit, and conventionally we treat electron as a negative charge and current is directed in flow direction of positive charge. Electric current in circuit is measured by an instrument called ampere meter or ammeter. For current measurement in an electric circuit, ammeter is connected in series with the load of which we have to measure current, and an ideal ammeter got zero internal resistance, so that during measurement it doesn't produce voltage drop across it and give error-free readings without any loading effect. Ohm's law, V is equal to IR, is a relation among voltage, current and resistance of an electric circuit, and this V is equal to IR or Ohm's law relation is first and foremost important understanding level of our subject electric circuit, and this law is given by George Simon Ohm in the year 1826. As per Ohm's law, the current flowing through any resistance or conductor is directly proportional to the voltage which is applied across this conductor, provided the physical condition of conduction such as internal structure of conductor or temperature, humidity of conductor remains the same, or we can say voltage which is applied across these two terminals of conductor and current flowing through this conductor are proportional to each other, and such proportional relation between current and voltage when graphically represented results in a straight line passing through origin as shown here, and all proportional relation can be converted into an equality relation using some constant, and the constant which we use to convert V proportional to I relation, voltage proportional to current relation is called as resistance of circuit, and our relation become V is equal to IR, and here R is a ratio of voltage applied across conductor and I current flowing through the conductor. And in this graphical presentation, when current is on vertical axis, the graph and horizontal line form a angle, and tangent theta of this angle is called slope of characteristic, and slope and resistance are inverse of each other, and all conductor which obey this Ohm's law relation relation got a linear straight line passing through origin, Vi characteristic are called ohmic resistors. And for an ohmic resistance, when voltage applied across conductor is doubled, current also get doubled. Both voltage and current got a proportional relation with each other. Proportional and linear current voltage relationship is possible only in ohmic resistor, whereas the current voltage relationship for solution of electrolytes or PN junction diode as shown here or filament lamp as shown here is non-linear. They are curved relationship between current and voltage, and such curve relationship represent some variation in physical condition of conduction, as in PN junction diode the depletion zone formed between P side and N doped side at PN junction reduce its width as we increase applied voltage, and due to that the slope of IV characteristic, which is inverse of resistance, change its magnitude, and such varying resistance is called as a dynamic resistance. And as slope of IV characteristic is increasing, the dynamic resistance of PN junction diode decreases as we increase applied forward bias voltage. Whereas in filament lamp, when applied voltage is small, the current flowing through the lamp is also small, and smaller operating temperature have a small amount of resistance, and as applied voltage increases, the increased current increase heating of filament, and increased temperature increase resistance of tungsten filament lamp, and the slope of this characteristic decreases to show an increase in resistance. So such varying resistance are defined in differential format and are called as a dynamic resistance. So Ohm's law is not obeyed in solution of electrolytes or PN junction diode or filament lamp, and resistance is not constant, whereas in an ohmic resistance, when we increase voltage to certain fold, the current also increases with the same multiple factor, and the ratio of voltage to current at all voltage and current values remains the same. Physically, resistance is the property of conductor material which oppose flow of current in it, and in fact this opposition of current flow basically become a demand for proportional voltage to make circulation of current, and in the process voltage source has to perform work, and in a resistance such work done by potential source in circulation of current get converted into heat. We can understand the physical property of resistance as opposition to flow of drift moving electrons by a microscopic study, and we know in a metallic conductor free outer orbital electrons randomly roam with a very high thermal velocity 10⁵ meter per second, and in a very small time 10⁻⁻14 second they have collisions, and by each collisions they divert their directions, and the motion of such thermal moving electron is perfect random, and an electron which start random thermal motion got frequent collisions and come back to the same position, and the resultant charge transfer by such thermal motion is zero. We can also understand the same phenomena as we have a certain cross section in conductor, and in a finite time interval the number of electron crossing this area from one side to another side is identical to number of electron crossing the same cross section from other side to this side, and net charge transfer by the thermal motion of random moving free electron is zero. The thermal motion of free electron is perfect random, and by several and frequent collisions it changes its direction and come back to the initial position, and there could be difference in random movement and collision pattern, but the fact is that such thermal movement become a perfect random phenomena and electron come back to the same position whatsoever the thermal random movement of electron may be. But in the same conductor, when external source voltage is applied, then voltage V across L length of conductor generate a potential gradient and an electric field, and the electric field is directed from high potential to low potential in conductor, and electron being negatively charged particle experience a force, and force on electronic charge is equal to charge and strength of electric field, and due to force all free electron exert an acceleration given as force per unit mass. The direction of force force and acceleration is opposite to direction of electric field intensity as electron possess negative charge, and due to force and acceleration the earlier random thermal motion of electron, which won't have any net charge transfer, get modified, and the modified movement of free electron shown by these red arrow directions got a net drift displacement from its initial position opposite to the direction of electric field. And the interesting fact is that the random motion behavior of two free electrons may be different, but the drift movement of all free electrons is in the same direction with the same drift velocity, and during this movement the drift moving free electrons get collided with other electrons, atoms, impurities, and in all collisions the kinetic energy gained by drift moving electron by the force and acceleration in electric field get transferred to material substance as heat, and we say these collisions are opposition to drift motion of electron, and these frequent collisions cause resistance in the current flow, and these collisions convert electrical energy into heat energy. The collision among thermal moving electrons is perfect elastic, and in this collision no energy exchange will take place, and only the direction of thermal motion get diverted, and the motion in a considerable duration can be treated as perfect random, and there is no net movement of electron by such thermal random motion. But when thermal motion of electron shown by black lines get modified by acceleration of electric field as shown by red lines, then the collision among electron involve exchange of energy, and in each such collisions the part of kinetic energy gained by electron in an acceleration in electric field get converted into heat energy within conductor material. Now the time between two collisions depends upon circumstances, and it is not fixed. When a collision takes place after a longer duration, more time is available to an electron for an acceleration, and when collision takes place in a smaller interval, electron can't make good amount of acceleration and velocity. So the average velocity of drift motion depends upon time between collision, and this time between collision is called as relaxation time. And if we assume that several drift moving electron, any number, got u1, u2, u3 initial random thermal velocity, and they have collision in t1, t2 and t3 time, and before collision there exists an acceleration in the opposite direction of electric field that makes a drift velocity component in a specified direction, and if we take average velocity of all those electrons at the time of collision, we found that sum of thermal random velocity of all these electrons is 0, and average time of collision is known as a relaxation time. So we can say drift velocity is directly proportional to relaxation time or time of acceleration between collisions, and in place of acceleration we can write force divided by mass, and force is charge of electron multiplied by electric field intensity, and this charge to mass ratio multiplied by relaxation time become another constant, and that constant mu e tau by m, where tau is relaxation time, is known as mobility of drift moving electron, and we can say drift velocity of electron is directly proportional to applied electric field across conductor, and proportionality constant is called as mobility, and mobility depends upon time between collisions called as relaxation time, which is roughly of the order of 10 to the power minus 14 second, and charge to mass ratio, specific charge of electron, is of the order of 10 to the power 11. So we can say mobility is of the order of 10 to the power minus 3. That means if we apply an electric field of 1 volt per meter strength, then the drift velocity of those accelerated electron in opposite direction of electric field is of the order of few millimeter per second only. Relaxation time or mobility of conductor depends upon internal atomic structure of crystal, and due to negligible mass inertia effect of free electrons, the relaxation time or mobility doesn't depend upon conductor geometry. Now we can define mobility as magnitude of drift velocity per unit of applied electric field, and its unit is velocity is meter per second and electric field intensity is volt per meter. So the unit of mobility is meter square per volt second. The thermal random motion of electron got different behavior, but all such random behavior got net zero displacement. But when potential difference is applied, the random thermal behavior of electron movement get modified, and all free electrons will drift in the same direction with the same velocity, and the drift velocity of free electrons is directly proportional to applied electric field. Consider a conductor of L length and A cross section area having n number of free electron per unit volume, and when we apply a potential of V volt across L length, the potential per unit length or potential gradient generate an electric field strength in the direction of high potential to low potential, and all free electrons will have force and acceleration in the direction opposite to electric field, and now all free electrons will drift in the same direction with the same average velocity. The interesting fact is, even with force and acceleration on free electrons due to frequent collisions among thermal movements of electron, the velocity of drift moving electron will not increase with time, but it will attain a stable constant value proportional to applied electric field. An electron having drift velocity Vd opposite to the direction of electric field will make a displacement delta x in a small time interval delta t, and dx is velocity multiplied by time. Now all electrons will drift in the same direction with same velocity, so all electrons which are at cross section plane S1 will drift to a new plane which is delta x ahead of it on S2, and in the meantime all electrons which are within this volume between S1 and S2 surface also drift by the same amount and cross this S2 surface from one side to another side, and if number density or number of free electrons per unit volume is small n, and this cross section area A and this displacement delta x has a volume A delta x, then this is the total number of electron which has crossed S2 cross section plane in delta t time, and in place of delta x displacement we can write drift velocity multiplied by elemental time. So the total amount of charge which has crossed S2 cross section plane can be obtained by multiplying number of electron crossing S2 surface in delta t time and charge of electron, and we can find out charge flow across S2 cross section surface is NEA Vd delta t, where Vd is drift velocity of electron, A is cross section area of conductor, N is number of free electrons per unit volume, and E is electronic charge. When all free electron drift with the same identical drift velocity, then in delta t time they would have a displacement delta x, and this displacement multiplied by cross section area become the volume of electron which has displaced across S2 surface area, and in this volume the number of electron is given by charge density multiplied by volume of S1 S2 area, and if electron got E charge, then the total amount of charge crossed S2 surface plane in delta t time is NEA Vd delta t, and charge transfer divided by time is rate of charge transfer, that is current, and this delta t get cancel out and will get current expression as NEA Vd, where N is free electron number density, E is electronic charge, A is cross section area, and Vd is drift velocity of electron, and this expression clearly indicate that in a conductor having more number of charge carrier per unit volume, there would be more current flow. Higher the cross section area of conductor available, more would be the current across conductor, and higher the drift velocity of electrons, higher would be the current flow, and we know drift velocity is directly proportional to applied electric field, and proportionality constant is called as mobility. So here in this current expression, if current per unit area or current density is obtained, then we'll get that this is Ne mu E, and this N E mu, all three are constant, and the product of these three constant is another constant known as conductivity of conductor, and we can say current density J is directly proportional to applied electric field in conductor, and proportionality constant is conductivity, and J is equal to sigma E is the Ohm's law in vector form, where J current density and electric field intensity both are vectors of proportional magnitude and the same direction, and we know applied electric field is voltage gradient or voltage applied per unit length, and in place of E when we write V by L, and in place of current density when we write I upon A, we can get a new format of V is equal to I 1 over sigma LA relation. 1 over sigma, inverse of conductivity is resistivity, and we got a relation V is equal to I rho L by A, and this rho L by A become a new constant known as resistance of conductor. So we can get Ohm's law, V is equal to IR, where R is opposition to current flow by collision among electrons, and this resistance is directly proportional to length of conductor, inversely proportional to area of cross section, and proportionality constant of resistance with geometry is called as resistivity, and resistivity is inverse of conductivity, and conductivity is product of free electron density, electronic charge, and mobility. Now Ohm's relation V is equal to IR can be modified as resistance equal to voltage to current ratio, and this ratio for a ohmic resistance where physical condition of conduction remains the same and voltage and current got a proportional linear relation passing through origin, then in that this resistance doesn't depend upon value of voltage and current, as here a voltage of 5 volt produce 0.5 ampere current, and applied voltage and current through ratio is 10 ohm, and if voltage is increased to say 7 volt value, the current also increase proportionally from 0.5 to 0.7 ampere, and the new voltage to current ratio remains the same. So this resistance doesn't depend upon applied voltage or current through, but it do depend upon resistivity, conductor length, and cross section area as shown by this relation in blue frame and yellow highlight. And here this resistivity depends upon nature of material, the internal structure of material, and physical conditions like temperature. And apart from resistivity, resistance also depends on geometry. Resistance is directly proportional to length of conductor, and if length become n times with same cross section area and same resistivity, resistance become n times. Now here resistivity is inverse of conductivity, and it depends upon nature of material, internal structure of material, and temperature like parameter which decide time between collision or mobility. So conductivity depends upon number of free electron per unit volume and mobility, and it doesn't depend upon geometry of conductor or the resistance value. This numerical example will explain the concept of mobility, drift velocity, conductivity, and resistivity. It is given that when 5 volt potential difference is applied across a wire of length 0.1 meter, then the drift velocity of electron in conductor is 2.5 into 10 to the power minus 4 meter per second. Look, this drift velocity is very small compared to thermal velocity. Thermal velocity is 10 to the power 5 meter per second, whereas drift velocity is 10 to the power minus 4 meter per second. Now, if the electron density in conductor wire is 8 into 10 to the power 28 per meter cube, then we have to calculate the resistivity of wire material. Now look, this number density of free electrons is so high that small drift velocity can generate good enough of charge transfer or current magnitude from given data. Applied voltage is 5 volt, number of electron per unit volume is 8 into 10 to the power 28, drift velocity is given 2.5 into 10 to the power minus 4 meter per second, and length of conductor is 0.1 meter. From applied voltage and length we can find out electric field intensity produced by source voltage in conductor, and it is voltage gradient or voltage per unit length, and when 5 volt is divided by 0.1 meter, then we'll get electric field strength as 50 volt per meter. That's a considerable electric field strength applied in conductor wire. Now drift velocity of moving electron is directly proportional to applied electric field, and from this proportionality relation the proportionality constant mu can be obtained as drift velocity per unit of applied electric field strength. Drift velocity is 2.5 into 10 to the power minus 4, and applied electric field is 50 volt per meter, and this ratio calculation results in mobility equal to 0.5 into 10 to the power minus 5, and mobility unit is meter square per volt second. And we know the conductivity is any mu where n is number of free electrons per unit volume, 8 into 10 to the power 28 given in this case. E is electronic charge, 1.6 into 10 to the power minus 19 coulomb. Mu is mobility calculated as 0.5 into 10 to the power minus 5 meter square per volt second. And inverse of conductivity is resistivity, and we have to calculate resistivity, and when we make calculation we find that resistivity of this wire is 1.56 into 10 to the power minus 5 ohm meter. This small numerical will explain relation of resistance with resistivity and geometry parameter R is equal to rho L by A. We are given that a small current is passing through a wire of length 15 meter of uniform cross section area 6 into 10 to the power minus 7 meter square, and resistance is obtained by measurement of voltage and current as ratio 5 ohm. Now we have to find out resistivity of material at that temperature at which these measurements are made. Now given length is 15 meter, cross section area is 6 into 10 to the power minus 7 meter square, and resistance is observed as 5 ohm, and resistance, resistivity and length area relation is R is equal to rho L by A, and this is modified as resistivity is R resistance multiplied by area divided by length of conductor. Resistance is 5 ohm, area of cross section is 6 into 10 to the power minus 7 given, and length is 15 meter, and calculation results as resistivity value of 2 into 10 to the power minus 7 ohm into meter. This important problem will explain relation of resistance and resistivity with geometry parameter, and it is given that if a copper rectangle rod of uniform cross section area having resistance R is wire drawn by mechanical pressure when a rod is passed through rollers, its length get elongated by 40% amount, and in this 40% longer wire, what is change of resistance and resistivity? Since during rolling material internal structure and physical condition like temperature are not changed, so with change of these geometric parameter, the resistivity of wire will not change. So resistivity will remain same even when by wire drawing the length of wire get increased by 40%. Since by rolling process when new length become 1.4 times initial length, no material is added, so the volume of material will remain constant, and volume is product of length and cross section area. So new length and new cross section area got same product as initial length and area. So new area in terms of initial area is given by this relation, and the length ratio is given. New length is 1.4 times initial length. So ratio of new area and initial area is equal to 1/1.4, and we know resistance is directly proportional to length and inversely proportional to area. So R2 is rho L2 over A2, and R1 directly proportional to length L1 and inversely proportional to area A1 is rho L1 A1, and since material got same resistivity and that get cancel out, so resistance ratio is ratio of length and inverse ratio of area. Now length got a ratio of 1.4 and inverse of area ratio is 1.4, so resistance become 1.4 multiplied by 1.4, 1.96. So 40% increase in length results in 96% increase in resistance with constant volume and constant resistivity. We hope this learning video has explained Ohm's law in complete detail, and now you understand microscopic behavior of drift motion of free electrons and the concept of mobility, conductivity and resistivity, and also got familiar with numerical calculation and dependency of resistance and resistivity with different geometry parameters. Our other videos of the same playlist will enhance your physics understanding and remove all sort of confusion and improve your scoring ability. If you found this learning work useful, do share it with your friends. Happy learning. Thank you very much.